Right now, a vast opening has formed on the face of our Sun, a dark chasm approximately 50 times the size of Earth. This feature is not just a distant spectacle, it is pointed directly toward our planet. From this void, an unseen river of charged particles is flowing outward at speeds exceeding 600 kilometers per second. This is not a sudden assault. For 14 consecutive days, this stream has been quietly hammering our world's magnetic defenses, leading NOAA to issue a G2 geomagnetic storm watch. Yet, the immediate alert is not the most unsettling part of this story. This phenomenon is not a singular event, but a recurring weapon, set to return with clockwork precision every 27 days. This recurring pattern forces us to consider not just the storm of today, but the cumulative stress of many storms to come. Following these developments on calm space will be essential for understanding what the next cycle of data reveals. What makes this event so unusual is its profound silence. There was no brilliant solar flare, no colossal explosion, and no incandescent arc of plasma detaching itself from the Sun to journey across the 93 million miles of empty space toward Earth. Normally, such a warning would follow a spectacular and violent solar outburst. By all the dramatic metrics that typically signal impending solar danger, our star appeared calm, almost boring. Despite this apparent tranquility, a team of forecasters at the National Oceanic and Atmospheric Administration's Space Weather Prediction Center in Boulder, Colorado, took a significant and deliberate step. They issued a G2 level geomagnetic storm watch, a formal warning of a storm that had no visible harbinger. Their decision suggests they saw something in the data that transcended simple visual observation. A G2 storm watch is a serious matter, and for anyone who follows solar weather, issuing one without a clear trigger is deeply strange. This is not a minor advisory. It is the kind of notification that puts utility companies on alert and has satellite operators forwarding memos to their engineering teams. It is a clear signal that Earth's magnetic field, our planetary shield, is braced for a significant impact. It means the delicate dance between the solar wind and our magnetosphere is about to become a turbulent confrontation. Yet, the central mystery remains. This powerful punch is arriving without a fist. The usual suspects, a coronal mass ejection or a solar flare, have been ruled out, as all recent eruptions were pointed elsewhere. If there is no blast, what exactly has the world's leading forecasters so concerned? The first clues lie within the numbers, and the data reveals a story of dramatic change. The solar wind, the continuous stream of particles that always flows from the Sun, has been maintaining a relatively placid background speed of around 340 kilometers per second. This is the Sun's ambient breath on an average day. However, forecasters anticipate a sudden and powerful surge, with wind speeds expected to accelerate past 600 kilometers per second, potentially climbing all the way to 700. This is not a gentle increase. It is a sudden, near doubling of speed, and it is happening without any of the conventional explosive triggers we would expect to see. Another critical indicator, the KP index, reinforces the strangeness of this event. This scale acts as a planetary seismograph for geomagnetic activity, and for days, it has been registering near zero, a sign of exceptionally calm conditions. Yet, in a span of less than 12 hours, forecasts project this value will leap from a near flatline reading to a KP of 6. A KP 6 signifies an active geomagnetic storm. It is the threshold where auroras push down into latitudes that do not normally see them, where GPS signals can become flaky, and where power grid operators begin paying much closer attention. A transition this rapid and this violent is rare and typically requires the brute force of a solar blast wave slamming into our magnetic field. Except, in this case, there is no blast wave. With no explosive cloud to blame, we are left with only what forecasters are calling a clean high-speed stream event. The word clean is crucial here, as it signifies an absence of the chaotic debris associated with a solar eruption. The source of this disturbance is not a violent, one-time explosion. Instead, the origin is a persistent feature that has been quietly sitting on the sun's surface for days, growing in size and slowly rotating into a direct line with Earth. The source is a coronal hole, a feature whose true nature is often misunderstood but is central to this entire event. Yet, there is a deeper layer to this story that has not been making headlines, and it fundamentally changes how we should perceive the coming days. While the world was watching for flares, the radiation environment around our planet was already being hammered. For 14 straight days, long before this new warning was issued, the flux of high-energy electrons in the outer radiation belt has been elevated. Particles measured above 2 mega-electron volts have remained above the 1,000 particle flux unit threshold, a key boundary indicating a hazardous environment for orbital technology. This is not a momentary spike, it is a sustained, relentless bombardment, with recent peaks climbing to between 1,700 and 3,200 PFU. These figures, while abstract, translate into a tangible threat for our orbital infrastructure. When a satellite is immersed in this high-energy environment for days on end, the particles do not simply pass through. Like water seeping into a foundation, these electrons burrow into insulation and build up inside sensitive components, accumulating a static charge. Eventually, that charge must go somewhere. It can discharge in a sudden arc, an internal, miniature lightning strike that can fry circuits, corrupt memory, and cause instruments to malfunction in ways that appear from the ground as random, inexplicable anomalies. The longer the exposure, the greater the risk of such a damaging discharge. This brings us to the heart of the current situation. The incoming stream is not impacting a rested system. Earth's orbital assets are already saturated, soaking in a radiation bath that has persisted for 2 weeks. In the coming hours, they are about to be hit with the full force of the stream itself. This is not a one-shot event. Unlike a cloud of plasma from a CME, which is a relatively brief sprint that sweeps past in about 12 hours, a high-speed stream from a coronal hole is a marathon. It can last for 3 to 5 days, sometimes longer. This creates a period of unrelenting pressure, the initial compression, the disturbance, and then day after day of elevated solar wind and electron flux, giving the magnetosphere no time to settle and recover. It is this sustained assault on a pre-stressed system that defines the true challenge ahead. There is a detail in all of this that should give us pause. The exact solar structure that is now aimed at our planet was in the same position just 27 days ago, and 27 days before that, and so on. This is not a random occurrence. It is a predictable pattern, one that is woven into the very fabric of the sun's own rotation. Yet, for all its predictability, for all that it can be measured, tracked, and modeled, this phenomenon remains a threat that has largely escaped public awareness. Our modern world is built upon a foundation of satellites. The location services in our phones, the precise timing signals that keep global financial markets in sync, the communication networks for emergency responders, and the weather forecasts that guide agriculture and aviation. All of these systems rely on a delicate constellation of technology orbiting in a hostile environment. And right now, that environment is being subjected to a stressor that few have ever heard of. It is a threat that does not appear dramatic in a typical image of the sun, yet it returns on a reliable schedule. The more we study it, the more it seems this may not be an isolated problem, but the beginning of a cycle that is only just now revealing its true nature. If you were to view an image of the sun in extreme ultraviolet light, such as those captured by NASA's Solar Dynamics Observatory, you would notice something that seems fundamentally wrong. A vast, dark region sprawls across the solar disk, an inky stain that appears to disrupt the otherwise glowing surface of plasma, almost as if a piece of the sun had been carved away. It is natural to look at these images and arrive at an obvious, yet mistaken, conclusion. That this is a sign of damage, a wound, or evidence that something has gone missing from our star. The language we use certainly doesn't help clarify the situation. We call these features coronal holes, and the word hole itself implies a void, an absence, a gap where something ought to be. This simple term, however, paints a deeply misleading picture of what is actually taking place. The truth of the matter is far more subtle and profound. A coronal hole is not a hole at all. There is no missing chunk of the sun, and no material has vanished. Deep within its core, our star continues its timeless work, fusing hydrogen into helium at 15 million degrees Celsius, just as it has for the last 4.5 billion years. What you are observing in that dark patch is not a gap in the sun itself, but rather a profound change in the structure and behavior of its magnetic field. Once you grasp this single concept, everything else about this recurring threat and why it is so different from the sun's other outbursts begins to fall into place. It is a shift in perspective that unlocks the entire mystery. To understand this, we must first consider the sun's magnetic field, which is not a simple, uniform shield. Instead, it is a tangled and chaotic web of magnetic lines that constantly shift, looping out from the solar surface, arcing through the atmosphere, the corona, and then returning back down. In most regions of the sun, these magnetic field lines are described as closed. They emerge from one point, curve through the corona, and dive back into another point nearby. This is much like the magnetic field of a simple bar magnet, where the lines elegantly loop from one pole to the other. When these field lines are closed, they effectively form a cage, trapping the superheated plasma of the sun's corona. This containment keeps the plasma dense, and because dense plasma glows intensely in extreme ultraviolet light, it is the reason most of the sun appears so bright in our images. In a coronal hole, however, something entirely different is happening. The magnetic field lines are not closed, they are open. They emerge from the sun, and instead of looping back down, they stretch outward, extending deep into space and across the solar system. In these regions, there is no magnetic cage, there is no trap, there is nothing to hold the coronal plasma in place. When that plasma finds itself situated atop one of these open magnetic field lines, it does the only thing it can. It flows. It streams away from the sun, following the path of the field line and pouring into the solar system at incredible speeds, sometimes exceeding 800 kilometers per second. This material is not being violently launched or ejected, it is simply being released into space. This continuous outflow is precisely why a coronal hole appears dark. The darkness is not a sign that the sun is missing, but rather that the plasma that would normally be there has already departed. It has drained away through those open magnetic gateways. As a result, the region has a lower density and a lower temperature, causing it to emit far less light in the wavelengths our observatories are designed to see. On our screens, it registers as a black void, a hole, but in reality, it is something far stranger and more dynamic. It is an open gate, a magnetic highway, leading away from the Sunday. Perhaps the most accurate metaphor is to think of it as an exhaust vent for the solar atmosphere, a place where the sun is continuously breathing its plasma out into the cosmos, for as long as that magnetic structure remains stable. And this is where the story becomes particularly compelling, because coronal holes are remarkably stable structures. A coronal mass ejection, by comparison, is a singular event. It is an eruption that happens once, blasting material into space before it is gone. Hours later, the sun has moved on. A coronal hole, on the other hand, is a persistent feature of the solar magnetic field that can last for weeks or even months. There are records of coronal holes that have been tracked across multiple solar rotations, vanishing as they turn to the far side of the Sun, only to reappear on the near side 27 days later, still pouring out a steady stream of high-speed solar wind. The coronal hole currently oriented toward us is not a new development. It has been there, quietly active, and we only take special notice when its position aligns with Earth. This alignment is critical because the solar wind does not spray out from the Sun equally in all directions. It flows in a focused stream along those open magnetic field lines, a stream that is anchored to the hole's location on the solar surface. For that wind to impact our planet, the hole must be positioned so that its output intersects with our orbital path. Thanks to the Sun's rotation, this alignment is temporary, usually lasting for a few days before the hole rotates out of our line of fire. But as the rotation continues, it will bring the hole back around 27 days later, and the alignment and the resulting solar storm will happen all over again. What is essential to remember is the fundamental contrast in how these phenomena release their energy. A coronal mass ejection is an explosion, sudden, violent, and depositing an immense amount of material in a very short time before it is over. A coronal hole is its complete opposite. It is a leak, a steady, continuous, and almost patient outflow of particles that persists as long as the underlying magnetic structure is active. One is a sudden shock to our planet's systems, while the other is a relentless pressure, presenting a challenge of an entirely different and more enduring kind. The effect on our planet is not a single, sharp impact. Instead, it can be thought of as a sustained, 1-4-day pressure campaign against Earth's magnetic field. Because this process is quiet, without the dramatic flashes of light that typically capture our imagination and spread across social media, its significance is easily underestimated. But here lies a crucial distinction. The Sun is not the direct trigger of the storm. While it is certainly the source, the real action, the mechanism that actually slams into our magnetosphere, does not unfold on the Sun itself. It materializes in the vast expanse between our star and our world, in a region most people have never heard of. This is where two very different kinds of solar wind are destined to collide. And in that collision, in the specific way that fast wind overtakes slow wind, the true story of this storm begins. If the coronal hole is the origin point, then the force that transforms this potential into a tangible threat is something else entirely, a structure that builds as the wind travels across the solar system. We call it a co-rotating interaction region. To understand this cosmic process, we can look to a more familiar analogy. Picture a long, dark, and mostly empty highway at night. A slow-moving truck is traveling at a steady 40 miles per hour. Some distance behind it, a sports car is racing along at 100 miles per hour. The sports car is closing the gap quickly, but when it finally catches up to the slow truck, what happens? It is forced to brake and decelerate. Now, if the highway behind the sports car is crowded with other vehicles all moving at high speed, they too must slow down, stacking up behind one another. They compress into a denser, slower, more chaotic pocket of traffic. A wave of congestion forms, a front where density and disorder multiply. This simple terrestrial scene offers a surprisingly accurate model for what occurs in space. With some simplifications, this is what a co-rotating interaction region, or CIR, truly is. Though scientists use this term, it is largely unknown to the public. Yet it is the single most vital structure for understanding why a high-speed stream from a coronal hole causes a geomagnetic storm. As we have explored, the coronal hole itself is merely the source. From this opening, a torrent of fast solar wind is released, traveling at speeds of 600, 700, or even 800 kilometers per second. But the fast wind does not simply slam into Earth. If that were all that was happening, this stream would arrive, flow past our planet, and Earth's magnetic field would hardly register its passage. The problem arises because this fast wind is not traveling into empty space. It is rushing into a region already occupied by the slow solar wind. This background flow, the ordinary ambient wind emerging from the sun's closed magnetic regions, typically moves at a more leisurely 300 to 400 kilometers per second. This slow wind fills the space between the sun and Earth first. Now, the fast wind from the coronal hole is chasing it down from behind, setting the stage for a monumental collision. In any meaningful sense, the fast wind cannot simply pass through the slow wind. Instead, it rams into it, compressing it like a cosmic bulldozer. At the interface where these two winds meet, a remarkable transformation occurs. A region forms where the density of particles skyrockets, and the strength of the embedded magnetic field can double or even triple. This entire structure evolves into a kind of rolling shock front, plowing its way forward through the solar system. This is the co-rotating interaction region. This is the CIR, and this is what actually strikes our planet. It is not the coronal hole, nor is it the high-speed stream directly. The initial impact, the force that drives the storm and causes that sudden 12-hour leap from calm conditions to a KP6 event, is this compressed boundary zone between the slow and fast winds. Understanding this is so central because compression is what makes the solar wind geoeffective. It is what gives the wind the ability to couple its energy into Earth's magnetic field. Here, we find the secret ingredient. Our planet's magnetic shield is remarkably selective. It does not simply absorb energy from any solar wind that happens to pass by. For the wind to truly transfer its energy into our system, to generate auroras and storm the magnetosphere, the magnetic field carried within that wind must be oriented in a very specific way. Specifically, the north-south component of that field, which scientists refer to as the BZ component, must be pointing southward. When the solar wind possesses a southward BZ, its magnetic field lines can connect with Earth's northward-pointing magnetic field in a process known as magnetic reconnection. This reconnection is what effectively opens the gates, allowing a flood of energy to pour into our world. A co-rotating interaction region, it turns out, is exceptionally good at creating these conditions. The intense compression of the fast wind ramming into the slow wind scrambles the magnetic field, twisting and rotating it. In doing so, it often generates extended periods of a southward field orientation, sometimes lasting for many hours at a time. This is why the most powerful initial phase of a storm from a high-speed stream often occurs right at the arrival of the CIR, not at the moment of peak wind speed. The fastest particles might arrive a day later, but the most disturbed magnetosphere usually coincides with the arrival of the shock front. The wave arrives, the compression hits, the field orients itself southward, the gate opens, and the storm begins. There is another factor that adds to this complex equation, and it relates to magnetic polarity. Coronal holes essentially come in two varieties, positive and negative, which is determined by the direction of the magnetic field embedded in their outflow. The coronal hole, currently directed toward Earth, is a negative polarity region. These negative polarity streams have a particular way of interacting with Earth's magnetic environment, especially at certain times of the year. When a negative polarity stream impacts our planet during the spring, around the March equinox and into April, its geometry aligns in a way that enhances its ability to cause geomagnetic disturbances. This phenomenon is known as the Russell-McFerrin effect. For now, what is important to recognize is that it is currently April, the polarity is negative, and the alignment is favorable, all of which stacks the odds in favor of a stronger than average response. The great challenge in all of this, and the reason forecasters are not more certain about the precise outcome, is that predicting the arrival of a CIR is genuinely difficult. The coronal hole itself is visible. We can see it, and we know its approximate size and location. However, The exact moment the compression front will arrive at Earth, how strong that front will be, and how long the crucial southward BZ conditions will persist are all subject to significant uncertainty. The solar wind is a turbulent and dynamic medium, which means that even with our most advanced models, its behavior can never be fully predicted. It serves as a reminder of the beautiful and humbling complexity of our solar system. The region of interaction where the solar wind meets our world is far from uniform. From a distance of 93 million miles, the fine magnetic details that determine whether a storm escalates to a KP5 or a more severe KP7 are simply beyond our ability to measure with precision. This inherent uncertainty is compounded by another challenge: the reliability of the very tools we depend on for our forecasts. Our Sentinel spacecraft, positioned at the L1 Lagrange point, about 1.5 million kilometers upstream from Earth, are designed to provide a crucial 30 to 60-minute warning of incoming solar weather. By sampling the solar wind before it reaches us, they measure its speed, density, and magnetic field orientation. However, recent observations have revealed anomalous spikes in the data readings that don't quite align with expectations. These signatures could point to instrument malfunctions, or they might indicate something genuinely unusual occurring within the approaching stream. The distinction is difficult to make. When your primary early warning system introduces noise into the signal, the capacity to predict the exact impact of an event becomes significantly degraded. So, while we know a stream is coming, and we understand its source, structure, and general timing, the precise severity of its peak and the exact moment of its arrival remain shrouded in doubt. And as this event draws closer, something else in the data is becoming clear, suggesting this particular disturbance will behave in a deeply unusual and rapid way. The forecast is about to shift from a quiet magnetosphere to a storming one with a speed that few outside of space weather circles are accustomed to seeing. This abruptness itself tells a story about how close to a tipping point our magnetic environment has been sitting all along. Imagine checking the weather forecast one morning to find that in just the last 12 hours, the temperature had leaped from a comfortable 65 degrees to a blistering 120. There was no gradual build-up, no extended warning, just a sudden, jarring flip. This is the kind of dramatic transition our planet's geomagnetic environment is about to undergo. This change won't happen in the atmosphere we breathe, but in the invisible magnetic shield that envelops our entire world, the KP index. A key measure of this environment is projected to jump from a placid 0.3 to a stormy 6 inches roughly 12 hours. This represents a nearly 6-point surge on a scale that only extends to 9. Such a rapid escalation demands a closer look at what this index truly represents. To grasp the significance of this event, one must first understand what the KP index is actually measuring. It is a global average of magnetic disturbance, calculated from the readings of 13 geomagnetic observatories strategically placed around the globe. When Earth's magnetic field is undisturbed, with nothing pushing against it, the instruments at these observatories barely register any movement. The KP index remains low, hovering near zero, which signifies that the space environment around our planet is stable. In this state, the magnetosphere is relaxed, and the electrical currents flowing through the upper atmosphere are minimal. A KP of 0 is the baseline of a calm planet. A KP of 6, in stark contrast, indicates a magnetosphere that is being actively and intensely agitated, as if it were a bell being rung. The currents have amplified, the auroras have expanded southward, and the electromagnetic stress placed upon every exposed system is orders of magnitude greater than it was just 12 hours before. Rapid transitions like this are not common, especially when they occur without the presence of a coronal mass ejection or CME. When a CME strikes Earth, Its arrival is often marked by a sudden shock, a powerful impulse that can shift the magnetosphere from quiet to violent in a matter of minutes. That is the expected physics of a blast wave smashing into our magnetic field. However, in the absence of a CME, as in the clean, high-speed stream scenario we are currently in, the transition is typically far more gradual. The co-rotating interaction region builds, the wind speed rises, and the field strength intensifies, all of which slowly ramp the system into a disturbed state over many hours. What makes the current forecast so notable is that the predicted KP jump is happening almost as fast as a storm driven by a CME. The system is responding as if it has been struck, even though no such impact has occurred. This curious behavior tells us something vital. The magnetosphere was already primed for a storm. The stage for this event was set long before the stream's arrival. Over the preceding 14 days, a period of elevated electron flux had been preloading the radiation belts, subtly stressing the system. This means Earth's magnetic environment has not truly been quiet. Instead, it has been carrying an invisible load, a hidden tension. When the co-rotating interaction region finally arrives, it does not need to exert much force to push the system over the threshold into a full-blown storm. It is because the system has been sitting just below that critical threshold for 2 weeks, waiting for the smallest additional push to tip it over the edge. This is the classic behavior of a threshold system. You can apply stress to a structure slowly and gradually over a long period, and to an outside observer, nothing appears to happen. The beams may bend slightly and the welds might groan, but the structure looks stable. Then, one day, you add just 1 more kilogram of weight, and the entire thing flips into a new state of failure. It is not that the final kilogram was the sole problem, it was merely the trigger. The real issue was the accumulated weight that came before it. This is precisely what is happening to our planet's magnetic shield. The incoming coronal wind is not the entire storm in itself. It is simply the final kilogram that tips the scales for a magnetosphere already under immense strain. As this stress mounts, a fundamental process known as magnetic reconnection is about to accelerate dramatically. Reconnection is the primary mechanism by which energy from the solar wind is transferred into Earth's space environment. When the interplanetary magnetic field, carried by the solar wind, tilts southward and makes contact with our planet's northward pointing magnetic field, the two fields do not simply pass by one another. Instead, they tear, break apart, and then reconfigure themselves into new arrangements. Each one of these reconnection events unleashes a burst of energy, which in turn accelerates particles and pushes plasma through the system. At normal quiet times, this process is a low-level, continuous background hum. During a geomagnetic storm, however, it becomes the dominant and most powerful force at play. The rate of reconnection at the front of the magnetosphere, the side facing the sun, accelerates exponentially. Energy floods into the system on the sunward side, while on the night side, within the long magnetotail, additional reconnection events fire off like a chain of lightning strikes. These events inject vast quantities of charged particles back toward Earth. From the ground, if you are at the right latitude under clear skies, this process manifests as the breathtaking beauty of the auroras. But for the satellites flying through it, the experience is one of a sudden and violent reorganization of their entire environment. The electrical currents flowing through the ionosphere amplify, the electrical landscape changes dramatically, and high-frequency radio propagation, which relies on bouncing signals off a stable ionosphere, becomes severely disrupted. On their journey from orbit to our devices, GPS signals must travel through the ionosphere, where they can be distorted and degraded. During a solar storm, these effects become more pronounced, especially at high latitudes, where radio communications can be disrupted for hours at a time. As a storm intensifies and the KP index climbs, These impacts spread to lower latitudes, affecting a wider range of systems across the globe. And yet, for all our understanding, forecasting the precise severity of these events remains a challenge. The current prediction points to a KP6 or a G2 level storm, but this is essentially a best guess. It is an estimate derived from models that project forward based on historical data from this same coronal hole's previous solar rotation. The forecast's uncertainty leaves us with a range of possibilities. If the coronal hole has expanded, or if the compression of the co-rotating interaction region is more intense, the storm could escalate. A prolonged period of southward-pointing magnetic field, the BZ component, or a higher density of solar wind could all push the event from a G2 into a strong G3 storm. At the G3 level, power grid operators begin actively managing their loads, and airlines may reroute flights away from polar regions. Conversely, the storm could also underperform. The arriving CIR might be weaker than anticipated, the magnetic field could shift northward sooner, or the peak wind speeds may not reach their projected values. This inherent unpredictability is the very nature of space weather. We can see a storm approaching, but its ultimate strength remains uncertain until it arrives. While much of the focus is on the immediate future, the 1-2 hour window of the storm's peak, whether the KP index will reach 6 or 7, or if the aurora will grace the skies of the northern United States, a far more prolonged event has been quietly unfolding. This other story, which has been developing for the past 2 weeks, has gone largely unnoticed amid the excitement for the coming storm. The true narrative, the one that provides crucial context for what is happening now, is not just about the next 12 hours. It is about a silent, invisible process that has been underway in Earth's radiation belts for 14 consecutive days. This raises a critical question. What has been happening in that unseen realm? During this entire period, satellites passing through these regions have been steadily accumulating radiation exposure, a factor that is often overlooked in the rush to predict auroral displays. As forecasters tracked the approaching CIR and the high-speed stream rotated into position, a separate, parallel storm has been building. This event has not captured headlines because it is not a visible phenomenon. It produces no brilliant auroras to be photographed from the ground. Instead, it is taking place in the vastness of the outer radiation belt, a region of space extending from approximately 13,000 to 60,000 kilometers above our planet. The intensity of this invisible storm is gauged in a measure unfamiliar to most, PFU, or particle flux units. Since April 3rd, these particle flux units have been documenting a significant and persistent event. For 14 straight days, the flux of high-energy electrons, specifically those above 2 megaelectron volts, a standard benchmark, has remained above 1000 PFU. To put this in perspective, this means the outer radiation belt, one of 2 donut-shaped zones of charged particles enveloping Earth, has been in a highly energized state for 2 full weeks. This level of activity is significant enough to cross the threshold where NOAA issues what are known as Alt-F3 alerts. These warnings are sent to satellite operators, advising them that their spacecraft face an elevated risk of internal charging events, and these alerts have been triggered repeatedly. The intensity of this event has seen impressive peaks. On several days during this period, the flux has surged to between 1,700 and 3,200 PFU, levels that are substantially above the alert threshold. This places unhardened electronics deep within a danger zone. However, the true concern is not just these momentary spikes in intensity, but rather the sheer duration of the event. A brief surge in radiation is a condition most modern satellites are designed to withstand. A continuous 1-4-day immersion in this harsh environment is an entirely different matter. This prolonged exposure creates the potential for slow, relentless, and invisible damage to accumulate within a satellite system's harm that may only become apparent weeks or even months later. To appreciate why this prolonged event is occurring, it is helpful to understand the nature of the outer radiation belt itself. Far from being static, these belts are highly dynamic environments. They consist of a constantly shifting population of charged particles, primarily electrons and protons, which become trapped by Earth's magnetic field. These particles are confined by the field's geometry, causing them to spiral along magnetic field lines, bounce between the north and south magnetic poles, and drift around the planet. The sheer complexity of this system is what makes it so fascinating to study. The number of particles within these belts is not fixed. It ebbs and flows as particles are energized and lost. The primary driver of these changes is the solar wind, which can either pump energy into the belts or drain it away. During periods of calm solar wind, the outer belt generally remains at moderate levels. However, when the solar wind becomes active, particularly with sustained periods of high speed and a variable magnetic field, the belts respond dramatically. This is when the electrons within the belt are accelerated, causing their energies to climb and the particle flux to increase. This acceleration is believed to happen through a complex interplay of magnetic waves and energy transfer from the solar wind, though the precise mechanisms are still an active area of research. The result, however, is clear. Active solar wind conditions lead to elevated electron flux, which is precisely the situation we have been observing. This is the crucial link that connects the prolonged 1-4-day radiation event to the approaching storm. The elevated flux is not a random background condition or a mere coincidence. It is almost certainly a direct consequence of the series of solar wind enhancements that have been washing over our planet in the days leading up to this moment. For some time, the coronal hole responsible for the current storm has been on the near side of the Sun, slowly rotating into alignment with Earth. In a sense, the space around our planet has been preconditioned by this activity, setting the stage for the main event that is now upon us. As it has rotated, the outer radiation belt has been responding to the shifting conditions upstream. It has been soaking up energy, accelerating electrons, and building a population of high-energy particles that now sits in wait for the main event. What happens next, when the co-rotating interaction region and its associated high-speed stream arrive, is difficult to predict. The incoming plasma will modulate this energized particle population in complex ways. Some of these events enhance the belts even further, pushing particle flux higher and intensifying the hazard of satellite charging. Yet others can actually deplete the belts, scattering electrons from their trapped orbits down into the atmosphere, where they are lost. Which of these outcomes will occur depends on the fine details of the incoming stream, its density, its magnetic field structure, and the duration of any southward BZ component. Without a clear forecast for those specifics, we cannot say for sure whether the radiation hazard will intensify or ease. What we do know is that the baseline has been elevated for 2 weeks, and the system has not had an opportunity to relax. Even if the belts are temporarily depleted during the storm's peak, they will likely re-energize in the following days as the tail of the high-speed stream continues to flow past Earth, feeding more energy into the magnetosphere. This brings us to the central story unfolding in our skies. The true narrative is not just the dramatic arrival of the CIR, the subsequent spike in the KP index, or the beautiful auroras that may follow. The deeper story is that Earth is now operating in a state where its radiation belts can remain energized for weeks at a time, not merely hours or days. With every recurrence of the coronal hole, another cycle of exposure is added. This raises a critical question about the long-term health of our orbital infrastructure. For the satellites flying through these belts, each one is aging faster than its designers anticipated. This accelerated, invisible degradation is not a flashy headline or a breaking news alert, but it is arguably the most significant consequence of the pattern we are watching unfold. And every 27 days, when the hole rotates back into view, it happens all over again. Part 6. The Satellite Fragility Problem. According to the current best estimate, there are approximately 11,800 active satellites in orbit around Earth. That number, 11,800, is not a misprint. A decade ago, such a figure would have seemed like science fiction. Today, it is simply the running total of what humanity has launched into the sky and has not yet allowed to fall back down. The majority of this growth stems from the explosive expansion of constellations in low Earth orbit over the last several years. Starlink alone accounts for thousands of these satellites, with OneWeb adding more. Amazon's Kuiper is beginning its deployment, and Chinese constellations are filling their own orbital shells. This density is steadily growing, with more hardware going up every month. What does all this have to do with the coronal hole? The connection is everything. These thousands of satellites are the very systems being slowly compromised by the recurring high-speed stream cycles we have been discussing. And the way they fail, when they do, is not what most people imagine. The common perception is of a satellite being blasted by a solar storm and instantly going dark, a dramatic, instantaneous death. But that is actually a rare occurrence. The more common scenario, and the one that is key to understanding the slow stress of these recurring events, is a phenomenon called deep dielectric charging. It represents one of the strangest and most insidious ways a spacecraft can die. Here is how the mechanism works. When high-energy electrons of the kind that populate the radiation belts strike a satellite, they don't just bounce off. They have enough energy to penetrate the spacecraft's skin, traveling several millimeters into its internal structure. If one of these electrons happens to strike a piece of insulation, a dielectric material inside the craft, it can become embedded, stopping its journey. This process repeats, and over hours, days, and weeks of continuous exposure, the buried charge accumulates. You cannot see it. You cannot measure it directly. In most cases, the satellite appears to be fine, operating normally and sending back telemetry that reports healthy values. But internally, the charge is growing, and the electric field across that dielectric is increasing. At some point, the dielectric material can no longer hold the accumulated charge. It breaks down. This results in an internal electrostatic discharge, a tiny bolt of lightning deep inside your satellite. That miniature lightning bolt can cause a number of problems. It might flip a memory bit, leading to a momentary error that the satellite's software can correct on its own. It could also damage a component, degrading the performance of an instrument in a way that is difficult to diagnose from the ground. In more serious cases, it can short a circuit, taking out an entire subsystem, and in the worst scenarios, it can trigger a cascade of failures that kills the spacecraft completely. The truly insidious part of this phenomenon is the timing of the discharge. It does not necessarily correspond to the peak of a storm. A discharge can happen days or even weeks after the radiation event has passed, because the charge is still buried in the dielectric, still building from the previous exposure, and just waiting for that final addition that breaches the threshold. This is what I mean when I say the satellite fragility problem connects directly to the central thread of this story. A single severe storm might produce a few manageable discharges across the entire fleet of 11,800 satellites. But what we are talking about here is not a single event. It is a recurring cycle. Every 27 days, the coronal hole rotates back into view. Every 27 days, the radiation belts get energized again. And every 27 days, a new wave of high-energy electrons drives into the dielectrics of every satellite in a vulnerable orbit. Critically, the charge from the previous cycle has not fully dissipated before the next one begins to pile on top of it. This is cumulative exposure. This is chronic stress. And it is precisely the kind of stress that modern satellite design, for the most part, was not optimized to handle. To put this into perspective, think about the incident in February of 2022 when SpaceX lost 40 newly launched Starlink satellites in a single geomagnetic storm. That was a dramatic, headline-grabbing loss that everyone covered. But those satellites were not lost because a solar flare vaporized them. They were lost because the storm expanded the thermosphere, which increased atmospheric drag on their low deployment orbit and pulled them down before they could boost to their operational altitude. That was a very different kind of failure, and it helps to illustrate the quiet nature of the threat we are discussing now. Beyond the dramatic headlines of satellite failures, a quieter and more insidious story is unfolding. This is the narrative of gradual degradation, where countless satellites are slowly being worn down by sustained exposure to the very solar events we are exploring. These are not spacecraft that have failed outright, but ones that now operate at a diminished capacity, their performance subtly compromised. Many of these satellites report recurring anomalies, glitches that align with uncanny precision to the 2-7-day rotation of the Sunday. This raises a critical question about the hidden vulnerabilities accumulating in our orbital infrastructure. This problem is magnified by the risk of cascading failures. A modern satellite is rarely a standalone object. It is a single node within a vast, interconnected network. The Starlink constellation, for instance, is not merely a collection of individual units, but a cohesive mesh. Each satellite communicates with its neighbors, relaying data through laser links and meticulously coordinating its orbit with the entire system. While the network is resilient enough to route around a single downed satellite, the failure of 20 or 200 could begin to unravel the integrity of the mesh in ways that are difficult to predict and repair. The global positioning system operates on a similar principle. GPS relies on a constellation of satellites, each of which must maintain timing accuracy to within nanoseconds for the system to function. If a solar storm were to disable enough of these satellites, or if ionospheric disturbances were to corrupt their timing signals, the precision of GPS-dependent systems on Earth would begin to decay, and its role extends far beyond simple navigation. GPS provides the essential timing backbone for our global financial markets, electrical power grids, and emergency communication networks, virtually every coordinated system underpinning the modern world. What remains deeply uncertain, and what we may not fully comprehend for years, is the sheer number of close calls that have already occurred. How many satellites have endured internal electrical discharges that brought them perilously close to complete failure? How many of their vital components have been weakened to the point that they will be the first to break during the next storm, even after surviving the last one? This information is rarely made public. Satellite operators treat anomaly data as proprietary, and incidents are seldom considered newsworthy unless they result in a major disruption of service. Consequently, our assessment of orbital fragility is fundamentally incomplete. We are aware of the dramatic failures that capture global attention, but we remain blind to the slow, steady erosion happening just beneath the surface. This gap in our knowledge means we may be systematically underestimating the true fragility of our systems in orbit. And so, the cycle repeats. Every 27 days, as the Sun completes its rotation, the coronal hole turns back toward Earth. The planet's radiation belts become energized, and the dielectric materials inside orbiting electronics once again begin to accumulate charge. With each pass, hardware that previously endured the stress is pushed a little closer to its operational limits. Eventually, for some of this hardware, a single cycle will be the one that finally pushes it over the edge. We will not know which satellite it will be, nor the precise moment it will happen, but with every rotation, the probability of a failure climbs. And more critically, the probability that this failure strikes a system the world truly depends on is climbing right along with it. To truly grasp this threat, we must understand the compounding effect of these phenomena. So far, we have discussed the radiation belts, satellite charging, and geomagnetic disturbances as if they were a simple sequence of events. A solar stream impacts the magnetosphere, which in turn responds, energizing the radiation belts and exposing satellites to radiation. While this chain of cause and effect is true, the underlying physics of the space environment is far more complex. The system is not linear. It is an intricate web of feedback loops. The radiation belts, geomagnetic storms, and solar wind conditions all interact with one another, producing outcomes that are exceptionally difficult to forecast. To appreciate this, we must move beyond simple models and embrace a more complex and dynamic reality. Consider this counterintuitive example. When a high-speed solar wind stream arrives, one might expect it to simply inject more energy into the radiation belts, causing the electron flux to steadily increase. This does occur on occasion, but it is not the only possible outcome. During many high-speed stream events, the belts actually deplete at the peak of the disturbance. The storm amplifies magnetic waves that scatter electrons out of their trapped orbits, causing them to fall into the upper atmosphere where they are lost. As a result, the radiation flux initially goes down. Then, in the days that follow, as the stream persists and conditions stabilize, the flux begins to rebuild, often surging to levels even higher than before the event began. This entire cycle loss, followed by recovery, and then enhancement, can unfold over 5 to 10 days from a single event. The effect is not minor. The flux can fluctuate by an order of magnitude or more, revealing a system far more dynamic than we might assume. This behavior is precisely what scientists refer to as a non-linear response. The system does not simply sum up its inputs and generate a proportional output. Instead, it possesses internal states and feedback mechanisms, meaning its reaction is contingent on the detailed history of what has occurred before. When you layer these high-speed stream events, one after another, each arriving every 27 days, while the effects of the previous one are still playing out, you create a system that is never allowed to reach equilibrium. The radiation belts are in a constant state of being energized, depleted, or re-energized. The magnetosphere perpetually carries a residual level of disturbance. In effect, Earth's space environment becomes chronically unsettled, a condition that our orbital infrastructure was never designed to withstand. This state of chronic disturbance runs contrary to the foundational principles of engineering design. Typically, engineers work by identifying a peak operational load and a failure threshold, then building a system capable of handling that peak load with an added margin of safety. This entire design philosophy is built on the assumption that such peak loads are rare, acute events. They arrive, they pass, and the system survives. Crucially, in the periods between these events, the system is expected to have time to recover, to cool off, and return to its baseline state. This is the logic we apply when designing everything from bridges and engines to airplanes and satellites. The assumption of rest and recovery is fundamental. But what happens when that core assumption is no longer valid? What occurs when the peak loads are no longer infrequent, but instead arrive every few weeks? What is the consequence when the recovery intervals shrink, becoming shorter than the time the system was designed to need to return to normal? The result is cumulative damage, a process known as fatigue. In materials engineering, metal fatigue is a well-documented phenomenon. A steel beam can easily support a load that is well below its ultimate yield strength if that load is applied just once. However, if you apply that same load repeatedly, cycling it on and off 10,000 times, the beam will eventually crack and fail at a stress level far below its static limit. The repetition itself becomes the mechanism of damage, as cumulative strain builds within the material's microstructure. It is a powerful analogy, suggesting that our space-based infrastructure may be susceptible to a similar process, an invisible weakening that precedes an eventual and perhaps inevitable failure. When we consider the wear and tear on a satellite, it's easy to imagine mechanical parts failing. But the more pervasive threat is often a subtler kind of exhaustion, a fatigue that is electrical, thermal, and even computational. Every anomaly a satellite's software must navigate, every unexpected surge it must handle, leaves a small, cumulative mark on its memory and components. Over time, these tiny changes accumulate. If this fatigue builds up more quickly than the system was designed to withstand, the consequences become starkly visible. Satellites may begin to fail long before their intended lifespan concludes. Entire constellations can suffer from attrition rates far higher than anticipated. And for those of us on the ground, services can degrade in ways that leave even the providers struggling to find an explanation. This reality forces us to ask a critical and perhaps underappreciated question. Is the vast infrastructure we have built in low, medium, and geostationary orbit truly resilient enough to withstand repeated coronal hole stream events over many years? The models we use to predict a satellite's operational lifetime are built on historical data, reflecting what happened during the last solar cycle and the one before it. But those past conditions may not be a reliable guide for what is to come. If the frequency of these high-speed streams intensifies as the solar cycle moves into its declining phase, a topic we will explore shortly, then the effective rate of degradation across our entire satellite fleet will also accelerate. The lifetime projections we have relied upon could prove to be profoundly optimistic. This is the compounding effect, and it reveals why a narrow, single-event view of space weather, simply checking the KP index on a given day, is insufficient. The true risk is not found in one isolated event, but in the relentless pattern, the cumulative sum of stresses, and the interplay between the system's state and the next wave of solar energy. The danger grows with every rotation of the sun. To understand the full scope of this phenomenon, we must pull back from low Earth orbit and look farther out. Everything we have discussed so far, the radiation belts, satellite charging, and geomagnetic storms, occurs within the protective embrace of Earth's magnetic field. This magnetosphere acts as a vital shield, deflecting the harshest radiation the sun sends our way. Yet, humanity is now venturing beyond this shield with renewed determination. NASA's Artemis program, along with a new generation of commercial lunar missions, marks our first sustained return to the moon in more than half a century. Once a spacecraft crosses the boundary of the magnetosphere and travels toward the moon, it loses that planetary protection. It becomes exposed to the full, raw environment of deep space. This environment is not merely characterized by occasional dramatic solar storms. It is a place of chronic background radiation, of elevated electron flux, and the slow, persistent pressure of the solar wind itself. The very same stream of particles about to impact Earth is also flowing past the moon. The radiation that preloads our satellites with dielectric charge is also bathing any spacecraft operating in lunar space. This leads to a question that has not yet been fully answered, one that the Artemis program is actively trying to solve. How do these recurring high-speed stream events affect human health during extended missions beyond the magnetosphere? Most of our data on space radiation comes from astronauts aboard the International Space Station, which remains safely inside the magnetosphere. We have far less information on chronic exposure outside this shield. The data we do possess, from the Apollo missions and a few lunar orbiters, was gathered during solar maximum conditions, a time when the solar wind was driven more by explosive coronal mass ejections than by these persistent coronal hole streams. This detail connects directly back to our central theme. If the solar cycle is indeed transitioning toward a period where coronal hole streams become dominant, then the radiation environment future lunar astronauts will face may be qualitatively different from what the Apollo crews experienced. It could be a more chronic and continuous exposure, less defined by acute storms and more by a steady, elevated level of radiation. The human health implications of such a shift, especially for missions lasting months or even years on or around the moon, are still being worked out. The key takeaway from this is that the recurrence of coronal hole events is not a problem confined to our planet's orbit. It extends outward, touching every mission we send into cislunar space, every astronaut on the lunar surface, and every deep space probe that must fly through that same stream every 27 days for the duration of its journey. The same persistence that makes these events a threat to satellites also makes them a critical factor in planning for human exploration. So, what is the mechanism that drives this relentless cycle? Here we find the piece that makes the entire story click into place, transforming our understanding from a story about a single storm into something far more structural and profound. The Sun rotates on its axis, completing one full turn approximately every 27 days as seen from Earth. Scientists call this the synodic rotation period, a term that accounts for the fact that Earth is also moving in its orbit while the Sun turns. This 7-day cycle, a monthly rhythm written into the fundamental mechanics of our star, is what turns a single coronal hole into a recurrence engine. Because the coronal hole is a structure anchored to the Sun, it rotates along with it. When the hole is on the near side, pointed toward Earth, the high-speed wind it generates streams directly toward us. As the Sun continues to turn, the hole rotates around to the far side, and the wind it produces is cast out into empty space away from our planet. Then, roughly 13.5 days later, the Sun's rotation begins to bring the hole back around to face us once more. If that structure is still there, and if it is still producing wind at a similar rate, and if its position is still aligned with Earth, we experience another stream. This triggers another storm, another round of radiation belt enhancement, and another wave of stress on our satellites and spacefaring systems. This predictable pattern is precisely what recurrence forecasting is all about. It is a simple, almost mechanical process, but its implications for our technological civilization are immense. Unlike the largely unpredictable nature of coronal mass ejections, the arrival of high-speed streams from persistent coronal holes can be forecasted with remarkable accuracy. This level of predictability might seem astonishing to those only familiar with the sudden violence of CMEs. The method is elegantly simple. One can look back at what occurred 27 days prior, corresponding to the Sun's rotational period. By checking if a coronal hole has survived its journey across the solar disk and its 2-week transit on the far side, and confirming its magnetic structure is stable, forecasters can project its effects into the future. Of course, this recurrence is not flawless. Coronal holes are dynamic. They can expand, contract, or even break apart. Yet, over the course of a few rotations, they exhibit a notable stability. A hole that has generated solar wind for several months will likely continue to do so, which is what allows us to speak of the April, May, and June events as a single, connected sequence. The coronal hole we are observing now, poised to send its stream of particles toward Earth's magnetosphere, is already a known recurring feature. It was present during the previous solar rotation and appears to have remained intact during its time away from our view. This raises a profound question about how we perceive solar threats. Barring any sudden and dramatic reorganization of its magnetic field, this same feature is expected to return in May and again in June, and possibly for several rotations after that. We are not simply witnessing an isolated event, we are observing a schedule. In a way, the Sun has already marked its calendar, and we are now able to read it. This shift in perspective, from a random event to a predictable pattern, is where the true nature of the risk begins to change. When you reframe space weather from a series of disconnected incidents to a cyclical pattern, the implications for our technology become far more complex. After a satellite is exposed to a single high-speed stream, it typically has a recovery period of about 30 days or more. During this time, any degradation to its systems can stabilize, internal electrical charges can dissipate, and any malfunctions can be diagnosed and managed. The system, in essence, gets a chance to breathe. However, when the next event in a recurring cycle arrives just 27 days later, with similar or even greater intensity, that breathing room vanishes. The residual effects from the first storm have not fully cleared before the second one begins to add its own impact. With each recurrence, this residual load accumulates, creating a compounding risk that grows over time. This accumulating risk is not distributed equally across the entire fleet of orbiting satellites. Some are inherently more vulnerable than others due to their orbital altitude, their path through different magnetic latitudes, or even the era in which they were designed. A spacecraft whose orbit regularly carries it through the heart of the outer radiation belt, for example, will feel the compounding effects of these recurring streams far more acutely than one in a lower, more protected orbit. Similarly, a satellite built with older electronics that have less radiation hardening is likely to fail much sooner than a newer, better shielded craft. The population of vulnerable assets is spread unevenly, and these recurring events will systematically find the weak points, picking off satellites in their order of vulnerability. These recurring cycles can be remarkably persistent. The historical record includes coronal holes that have remained active for 6, 8, or even 10 consecutive solar rotations. That translates to nearly 8 months of clockwork-like storms, arriving every 27 days to batter the same magnetosphere and compound their effects on the same group of satellites. While not every coronal hole lasts for such an extended period, enough do that the pattern is a well-established feature of space weather. We have been aware of this phenomenon since the 1960s and 1970s, when the Skylab Observatory first captured clear images of coronal holes in X-ray light. Those observations revealed them to be persistent, structured features, not just random, fleeting patches on the sun's surface. What has changed since the era of Skylab is not the sun. It continues to behave as it always has. What has changed is us. The density of our infrastructure in space has grown exponentially, and our global economy has become deeply dependent on it. This makes a multi-month campaign of recurring storms a far greater threat, capable of eroding the reliability of systems that modern life has come to treat as perpetually available. The sun's recurrence engine has been running all along. We are only now building enough critical infrastructure in its line of fire to truly feel the consequences. Let us now consider a direct comparison, placing two phenomena side by side, much like a lawyer presenting evidence to a jury. On one side, we have a coronal mass ejection, or CME. On the other, a high-speed stream from a coronal hole. Both are capable of producing geomagnetic storms that can reach the G2 level on the NOAA storm scale, and sometimes higher. Both can generate beautiful auroras, disrupt radio communications, induce currents in power grids, and place stress on satellites. By the standard G-scale metric that often captures public attention, they can appear quite similar. This naturally leads to a question: why do CMEs receive so much more focus, and is that attention truly warranted by the nature of the risk? To understand the distinction, we must look closer at their fundamental characteristics. A CME is, in essence, a solar explosion. It involves a massive chunk of the sun's outer atmosphere, a plasma cloud weighing perhaps 1 billion tons, being violently thrown from the surface. This material is accelerated to incredible speeds, in extreme cases exceeding 2,000 kilometers per second, and launched across the solar system. If a fast CME is aimed at Earth, it can bridge the distance from the sun in as little as 15 hours. Upon arrival, it slams into our planet's magnetosphere, driving a severe but typically short-lived storm that plays out over 6 to 24 hours. Afterward, the plasma cloud sweeps past, the storm subsides, and the magnetosphere recovers. The entire event, from arrival to recovery, might last only a day or two. The most famous solar storm in history, the Carrington event of 1859, was a CME. A high-speed stream from a coronal hole is different in nearly every one of these aspects, except for its potential peak intensity. The solar wind is not ejected in a single blast. It is streamed continuously over a period of multiple days. Its velocity is lower, generally topping out around 800 kilometers per second, compared to the 2,000 kilometers per second or more of the fastest CMEs. Consequently, the transit time from the Sun to Earth is longer, typically taking 2 to 3 days, rather than a matter of hours. When the storm arrives, it does not slam into the magnetosphere, but rather grinds against it. The geomagnetic activity, measured by the KP index, rises slowly over many hours and can remain at elevated levels for 1 or 2 full days. This sustained pressure allows the flux of energetic particles in the radiation belts to build steadily over the entire duration of the event, representing a fundamentally different kind of challenge. The cumulative stress placed upon satellites, when measured as integrated exposure, can paradoxically surpass the strain from a coronal mass ejection. This is true even when the CME has a higher peak intensity, simply because the exposure to a high-speed stream lasts so much longer. A helpful comparison is to think of a CME as a sudden, powerful punch, while a high-speed stream is more like a persistent, unending flood. The ability of our infrastructure, our satellites, power grids, and communication systems to withstand a punch depends on having a safety margin above that peak impact. In contrast, surviving a flood depends on the capacity for continuous drainage throughout the event. These are fundamentally different kinds of resilience, and it's a critical distinction. Historically, our infrastructure has been designed with greater attention to withstanding the punch, because CMEs were the source of headline-grabbing events and Carrington-class catastrophes. They were what engineering standards and emergency plans were written for. Yet, high-speed streams routinely generate G2 and G3 level storms. Over an entire solar cycle, they likely contribute more total stress to our space-based technology than CMEs do, and they are far from rare. A single large coronal hole can trigger storm-level conditions every 27 days for months on end, a persistence almost unheard of from CME-driven events. There is also a profound psychological component to this dynamic. As humans, we are evolutionarily wired to react to dramatic and visible threats. When a coronal mass ejection is captured by the coronagraphs aboard the SOHO spacecraft, it appears as what it is: a violent explosion, a vast, billowing cloud of plasma. It is something you can point to and immediately identify as the danger. A coronal hole, on the other hand, presents as just a dark, quiet patch on an image of the sun, a feature many might not even recognize as significant. It doesn't erupt or flash, it simply sits there, rotating with the sun, continuously streaming its solar wind. This subtle presentation fails to trigger the same instinctive alarm in our nervous systems. It seems our own cognitive wiring makes us susceptible to underestimating these quieter, more persistent dangers. Consequently, media coverage, public focus, and political resources all tend to skew toward the drama of CMEs, the visible, explosive events. The persistent, recurring, and slower threats often go under-examined. This discrepancy between the actual distribution of risk and our psychological distribution of attention represents one of the most significant failures in how we currently discuss space weather. We have become fixated on the photogenic threat, while discounting the wallpaper threat, the danger that is always present in the background. And it is this wallpaper threat, the high-speed stream from a coronal hole that returns every 27 days to slowly erode the health of our infrastructure, that may ultimately be the one to cause a critical failure. We may now be entering an era where this very threat is poised to dominate, because the Sun itself is changing. Solar cycle 25 is maturing, and its next phase will determine how the balance between CMEs and high-speed streams shifts in the years to come. Our Sun does not operate at a constant level of activity. It breathes through cycles. For at least 400 years, based on historical records and sunspot observations, it has followed an approximate one-year rhythm that governs the rise and fall of its energetic output. This fundamental pulse of our star sets the stage for all space weather. We are currently living through solar cycle 25, which officially began in December of 2019 as the previous cycle reached its minimum and the new one began to build. This particular cycle has been an interesting one to watch. It started with forecasts predicting another weak, below average maximum, similar to its predecessor. However, as it progressed, it consistently outperformed those early predictions. The sunspot count climbed higher than anticipated, the frequency of solar flares increased, and the number of coronal mass ejections ramped up. Now, it appears that the cycle reached its peak sometime around the middle of 2024, or perhaps slightly later. I use the word appears because pinpointing the exact peak of a solar cycle is an exercise best done in retrospect. Analysts must observe the Sun's activity for several months, or even a couple of years, after an apparent peak to confirm that it wasn't merely a temporary plateau. Nonetheless, most of the key indicators we follow, the monthly sunspot number, the 10.7 centimeters radio flux, and the rate of CME-driven geomagnetic storms all suggest that the maximum is now more likely in our recent past than in our future. It is this transition from the rising phase of the cycle to its declining phase that elevates the story of any single coronal hole into a much larger, more significant pattern. Historically, a clear pattern emerges. The rising phase of a solar cycle, the climb from minimum to maximum, is dominated by active regions and the coronal mass ejections they generate. The Sun is spotty, energetic, and its magnetic field is a tangled, chaotic mess that is constantly reorganizing itself. While coronal holes do exist during this phase, they are typically confined to the polar regions, directing their high-speed winds away from Earth's orbital plane. As a result, the geomagnetic storms during this period are driven mostly by CMEs. The declining phase, however, is different. As the cycle winds down toward its next minimum, the active regions become less numerous and the rate of CMEs decreases. The Sun's magnetic field begins to untangle, reorganizing itself into a simpler configuration. In this reorganization, something crucial happens. The coronal holes that were once confined to high latitudes begin to migrate toward lower latitudes. They stretch and expand, with some reaching all the way to the Sun's equator, forming what are known as trans-equatorial coronal holes. When a coronal hole is positioned near the Sun's equator, the high-speed wind it emits is perfectly aligned with the ecliptic plane, the very plane in which Earth orbits. This positioning makes these equatorial coronal holes maximally geo-effective. They can send their streams of solar wind directly toward our planet, rotation after rotation, for months at a time. This is the new face of space weather in the declining phase of a solar cycle. The explosive threats diminish, but the chronic threats increase. The number of powerful G4 and G5 storms may go down, but the frequency of recurring G1, G2, and G3 storms driven by coronal holes can actually go up. The overall rate of geomagnetic disturbance, when measured across an entire year, can remain high or even climb. The occasional, sharp spikes of CME impacts are replaced by the steady, relentless drumbeat of coronal hole events. The nature of the danger transforms, shifting from sudden shocks to a slow, methodical pressure on our technological world. If our Sun is indeed entering a new phase, with solar cycle 25 transitioning from its active period into its decline, then the events we are witnessing right now may be profoundly significant. This specific coronal hole stream could be an early indicator of the dominant space weather we can expect for the next several years. This wouldn't be an isolated event, but rather the opening chapter of a new regime, one where recurring high-speed streams become the primary driver of geomagnetic activity and the main source of stress on our satellite infrastructure. That represents a fundamental shift, though it is vital to be cautious here. Predicting the Sun's future behavior is an exceptionally challenging science. Our star has surprised us many times before. Cycles that appeared weak have suddenly become strong, and those that seem to have peaked have produced secondary bursts of activity. We have been wrong in our forecasts repeatedly. So, this is not a declaration that the next 5 years will be defined by coronal hole streams. It is, however, an observation that if this cycle follows a typical pattern, this is precisely what we would anticipate. The fact that we are already observing persistent, recurring coronal holes generating regular G2 level storms is entirely consistent with that expectation. For anyone operating satellites in low Earth orbit, or for those who depend on their services, this possibility must be factored into future planning. So much of the infrastructure built in the last decade has matured during the Sun's active phase. The declining phase is a different environment, and the longer it lasts, the more its unique conditions will become our new normal. There is another factor at play, one I touched on earlier, known as the Russell-McLaren effect. The particular negative polarity of the stream currently reaching us, combined with the time of year, creates a geometric alignment that naturally enhances the storm. First detailed by scientists Chris Russell and Robert McLaren in the 1970s, this effect describes how the seasonal tilt of Earth's magnetic axis relative to the Sun's interplanetary magnetic field changes how effectively different solar wind streams can disturb our magnetosphere. It's a reminder that space weather isn't just about what the Sun emits, but also about how Earth is positioned to receive it. The mechanics are elegantly simple. Earth's magnetic field is tilted in relation to its orbital plane. Because of this tilt and the structure of the interplanetary magnetic field, certain types of streams are more potent at delivering a southward BZ component, the key ingredient for a geomagnetic storm at specific times of the year. Negative polarity streams, like the one we are currently experiencing, find their impact amplified in the spring. In contrast, positive polarity streams are enhanced in the fall. This effect reaches its peak near the equinoxes in March and September, then diminishes as we move toward the solstices in June and December. We are now in mid-April, which is past the peak of this effect, but we remain well within a period where the geometry can still meaningfully contribute to geomagnetic activity. The storm we are about to experience is likely enhanced by this seasonal factor, not enough to transform a G2 storm into a G4, but enough to make the impact slightly stronger than an identical stream would produce in July. This has fascinating implications for how recurring solar events unfold over time. A coronal hole that remains active for several solar rotations will generate a series of events that are each subtly different. This isn't because the hole itself is changing, but because Earth's position in its orbit is constantly shifting. The event in April receives a boost from this geometry. A subsequent event in May would get a smaller boost. By June, that enhancement would be gone, and the very same stream might produce a weaker response. Then, looking ahead to September, if the hole was still active and its polarity hadn't flipped, we might see related positive polarity structures begin to receive their own boost as we enter the autumn equinox window. What this ultimately means is that even a predictable, recurring event is never the exact same event twice. The geometry of our orbit modulates it. The timing of its arrival can amplify or dampen its effect. For any given solar rotation, The response of Earth's systems depends on a complex combination of the stream itself and the orbital position we occupy when it arrives. This adds yet another layer of complexity to an already intricate picture. And it is one more reason why long-term forecasting is so difficult. It also underscores why this April event is so worthy of our close attention, as it is occurring during one of those geometrically favorable windows for producing stronger than average storms. Let us now turn our focus from the sun back to Earth and discuss what is truly at stake when a storm like this arrives. The entire reason we study space weather, why NOAA issues forecasts and engineers build monitoring spacecraft, is because the electromagnetic environment of near-Earth space is directly coupled to the technological systems that underpin our civilization, and the number of those systems has been multiplying rapidly. Consider the Global Positioning System, or GPS. Along with its international counterparts like Europe's Galileo, Russia's GLONASS, and China's Beidou, it forms the backbone of modern positioning, navigation, and timing. Your phone, your car's navigation, aviation, and global shipping all rely on it. Financial markets use it to timestamp trades with microsecond precision, while power grids use it to synchronize electrical currents across vast distances. It has woven itself so deeply into the fabric of society that most people are unaware of its presence until it falters. And GPS is vulnerable to geomagnetic storms, specifically through their effect on the ionosphere. This is a layer of our upper atmosphere, stretching from about 80 to 1,000 kilometers in altitude, where ultraviolet and X-ray radiation from the sun ionizes the air, creating a sea of plasma. Radio signals, including those from GPS satellites, must travel through this plasma to reach receivers on the ground. Under normal conditions, the ionosphere is relatively smooth and predictable, and its minor distortions to GPS signals can be easily corrected. During a geomagnetic storm, however, this layer becomes turbulent. The density of electrons fluctuates wildly, and structures known as ionospheric irregularities begin to form. These irregularities scatter radio signals in unpredictable ways, corrupting the very information our world depends on. When solar winds buffet our planet, the signals that guide our world can falter. They arrive at receivers delayed, degraded, and sometimes vanish completely. For our global positioning systems, this means the typical accuracy of a few meters can suddenly degrade to tens of meters or even more. For most of us, this is a minor frustration, a map on a phone taking a moment longer to find its place, or a rideshare driver appearing on the wrong street corner. But for professionals who depend on this precision, the consequences are far more severe. Precision agriculture, which uses centimeter-level GPS to steer tractors, can be forced to a standstill during a storm. Surveying work, where accuracy is paramount, becomes entirely unreliable. In aviation, precision landing procedures that depend on augmented GPS may become unavailable, forcing pilots to revert to older, less efficient instrument systems. These disruptions, though seemingly small, ripple through the economy, accumulating into a substantial hidden cost. The disturbance extends to our ability to communicate across vast distances. High-frequency radio, essential for long-haul aviation over oceans and polar regions, as well as for amateur radio operators and certain military communications, works by bouncing signals off the ionosphere. During a geomagnetic storm, however, this reflective layer can become absorptive, especially at high latitudes. The result is what's known as a polar cap absorption event, or more simply, a shortwave radio blackout. For airliners on polar routes, this can mean losing their primary link to air traffic control. They are then forced to rely on backup satellite systems or divert their course south to less disturbed skies. Such rerouting is not a simple detour. It costs precious time, burns additional fuel, and, during a prolonged event with repeated blackouts, can impose a significant financial burden on the global aviation industry. Our power grids are also exposed, threatened by a phenomenon known as geomagnetically induced currents, or GICs. As a geomagnetic storm warps Earth's magnetic field, this fluctuation induces electrical currents in long conductors on the surface. This includes the vast networks of high-voltage transmission lines that form the backbone of our electrical grid. These induced currents flow into the transformers at either end of the lines. The problem is that transformers are engineered to handle alternating current, AC, but a slowly varying GIC behaves much like direct current, DC. This unwanted DC pushes the transformer's core into saturation, which in turn distorts the AC waveform. This process creates harmonics that can cause the transformer to dangerously overheat, trigger protective relays to shut down power, or, in the most extreme cases, inflict permanent physical damage. The infamous Quebec blackout of March 1989 serves as a stark reminder of this vulnerability. A severe G5 class geomagnetic storm generated powerful GICs that overwhelmed the Hydro-Quebec grid, causing a system-wide collapse. The event plunged 6 million people into darkness for 9 hours. While the storm we face today may be far less intense, the underlying physical mechanism remains exactly the same. Even smaller storms produce smaller effects, and the cumulative stress they place on transformers can shorten their operational lifespan and accelerate their aging. This makes the entire grid more fragile over time, even if no single storm causes a catastrophic failure. Geography plays a critical role in this threat. GICs are significantly more powerful at high latitudes, where the planet's magnetic field lines are nearly vertical and the magnetic disturbance is most intense. This is why regions like Canada, Scandinavia, and the northern United States are particularly vulnerable. Over the decades, utilities in these areas have invested in mitigation strategies, installing monitoring systems, developing operational procedures for storm management, and hardening their most critical transformers. Yet, this investment is unevenly distributed. As the solar cycle moves into its declining phase, the frequency of storms is expected to rise, meaning the cumulative stress on the grid will only continue to climb, testing the limits of our preparedness. What connects all these vulnerabilities is the relentless rhythm of recurrence. If the coronal hole responsible for the storm persists, this cycle of disruption repeats roughly every 27 days. The ionosphere is agitated, transformers heat up, and satellites absorb another dose of radiation. Our modern world, built on the assumption of perpetually available infrastructure, must continuously absorb this accumulated stress. The result is not a sudden, dramatic catastrophe, but a gradual erosion of reliability. Services that were once dependable become intermittently flaky. Systems designed to last a decade begin failing after 7 years. Costs that were once minor line items compound into serious budgetary pressures. While the aggregate effects can be enormous, they are spread across so many systems and organizations that their true cause, the restless nature of our sun, is often overlooked. There is another, related problem that has grown in proportion to our presence in space, causing increasing concern among satellite operators. The challenge is that satellites do not simply orbit the Earth, they must be actively managed. Their positions must be tracked, their paths predicted, and their trajectories adjusted to avoid collisions with other satellites and with the ever-growing cloud of orbital debris. This raises a critical question. What happens when the very systems designed to protect these satellites are themselves vulnerable to the same space weather events? Low Earth orbit is far from empty. As we've discussed, it is home to over 11,800 active satellites, but they are vastly outnumbered by debris. Space debris tracking organizations are actively monitoring approximately 30,000 objects larger than 10 centimeters. Beyond that, they estimate there could be 1 million objects larger than 1 centimeter too small to be tracked reliably, but more than large enough to cause catastrophic damage in a collision. At orbital velocities of 7 to 8 kilometers per second, even a tiny 1 centimeter object carries the kinetic energy of a large caliber bullet. A direct hit can obliterate a satellite, instantly creating thousands of new fragments, each one a new hazard that increases the probability of future collisions. This frightening possibility leads to a catastrophic scenario known as the Kessler syndrome, first proposed by NASA scientist Donald Kessler in 1978. The theory posits that if the density of objects in low Earth orbit surpasses a critical threshold, collisions will begin to generate new debris faster than atmospheric drag can remove it. Each collision creates more projectiles, which in turn increases the likelihood of more collisions. The system could enter a runaway cascade, a chain reaction that could render entire orbital bands unusable for decades or even centuries. While the Kessler syndrome is a deeply sobering prospect, it is not yet a foregone conclusion. While the prospect of a cascading orbital debris event remains a possibility, most estimates suggest we have not yet crossed that critical threshold. We are, however, moving closer. Whether we cross that line depends not only on the sheer number of objects in orbit, but on our ability to prevent them from colliding. At present, collision avoidance relies on a complex and fragile chain of systems. It begins with ground-based radar and optical telescopes meticulously tracking orbital objects. This data is then compiled into vast catalogs, which are fed into analysis software to predict potential close approaches or conjunctions. When a risk is identified, satellite operators are alerted, decisions are made to maneuver, and thrusters are fired to steer spacecraft to safety. But this chain, for all its redundancies, is not without its vulnerabilities. For instance, solar storms can create ionospheric disturbances that interfere with ground-based tracking. The vital data links connecting tracking centers to satellite operators can become degraded. A satellite itself might enter a protective safe mode during a storm, rendering it unable to execute a crucial avoidance maneuver. Should a critical maneuver be required when an operator lacks reliable positioning data, the outcome could be the very collision the system was designed to prevent. Recent studies reveal a troubling trend. The probabilities of such collisions are climbing. Some researchers estimate that the likelihood of a major collision in low Earth orbit in the coming decade is significantly higher than it was just 10 years ago, a rise driven largely by the proliferation of satellite megaconstellations. Space weather events, which can degrade tracking and communications, act as multipliers on this baseline probability. They heighten the chance that, during a specific solar event, a maneuver might be delayed, an alert might not be received, or a dangerous conjunction might go entirely undetected. This brings us back to the central theme of our story, the recurring coronal hole. This persistent feature on the Sun creates precisely the kind of environment that elevates this risk. The danger doesn't stem from a single, powerful storm causing a collision directly. Instead, the threat lies in the accumulated pressure from repeated, smaller disruptions. For as long as the coronal hole remains, the entire collision avoidance infrastructure is stressed every 27 days. With each cycle, the probability of a near miss or a system failure inches slightly higher. Over a period of many months or even years of these recurring solar wind streams, the cumulative chance of at least one of these events escalating into an actual collision grows steadily. This is the principle behind the collision clock. It is not counting down to a predetermined doomsday, but rather ticking toward a threshold of probability, and this environment of recurring stress is causing it to tick ever faster. As these events unfold in space, it is worth noting something that has been happening here on Earth, though we must be exceptionally careful in how we frame the connection. Over the past week, significant severe weather outbreaks have occurred in several parts of the world, including tornado outbreaks in the United States and unseasonal storms in other regions. It is critical to state unequivocally that these events are not caused by the coronal hole. Geomagnetic storms and terrestrial weather systems are not linked in any direct way that could generate a tornado or a major thunderstorm. The physics governing our atmosphere and the dynamics of space weather operate on entirely different scales and through different mechanisms. The notion that solar activity directly drives weather on Earth is simply not supported by our current understanding. However, this coincidence of events introduces a valuable concept, that of compound risk. Compound risk describes a situation where multiple, independent stresses on different systems can combine, producing an overall impact on society that is far greater than the sum of its parts. Consider a severe weather outbreak that damages the power infrastructure in a given region. This is a significant problem on its own. Now, imagine a geomagnetic storm that simultaneously places the electrical grid under immense stress. This is also a problem on its own, but when both occur in the same week, affecting the same infrastructure, their total impact is not merely additive, it can become multiplicative. Repair crews may already be stretched thin, backup systems might already be engaged. The operational margin that utility companies normally rely on is eroded by the first event, leaving them with far less capacity to absorb the effects of the second. This is not to suggest that the coronal hole is causing severe weather, or that these events are somehow coordinated. They are independent phenomena that happen to be occurring in the same window by pure coincidence. Yet, the experience of navigating both simultaneously offers a glimpse into the reality of a world defined by increasingly interconnected stresses. This is not some hypothetical future, it is the world we already inhabit. The scientific term for this phenomenon is compound extremes, a concept that has been gaining attention within the climate change research community. The fundamental observation is that as the frequency of various extreme events rises, so too does the probability that multiple, distinct events will overlap in time and space. When they do, a society's capacity to respond is tested in ways that a single event never could. What this means for our central story is that the risk posed by recurring space weather does not exist in isolation. It sits alongside the risks of extreme weather, cyber attacks, pandemics, and all the other pressures modern societies must contend with. While any one of these risks might be manageable on its own, the wrong combination at the wrong time can overwhelm our collective ability to respond. The recurring coronal hole, by introducing a predictable, monthly stressor on our satellite and grid infrastructure, is one of these persistent background layers. It may not be the most dramatic threat, but it is there, cycling every 27 days and adding its contribution to the overall load our vital systems must carry. Everything we have discussed, from the behavior of the sun to the impacts on Earth, is predicated on our ability to see what the sun is doing. Our entire framework of understanding is built upon the data gathered by our network of satellite observatories, our ground-based magnetometers, and the in-situ monitors positioned in the vastness of space between our planet and its star. Together, these instruments generate the streams of information that are transformed into the forecasts guiding our response to events like the one currently unfolding. And while this observing system represents the most comprehensive space weather monitoring capability humanity has ever constructed, it is essential to honestly discuss its very real limitations. Our most crucial source of real-time monitoring of the solar wind as it approaches Earth comes from a small constellation of spacecraft. These sentinels are positioned at the L1 Lagrange point, a gravitationally stable location approximately 1.5 million kilometers upstream from our world. The fact that so much of our warning system depends on so few assets so far away highlights a potential vulnerability in our ability to see what's coming. At the L1 Lagrange point, our primary sentinels against the solar wind are the ACE spacecraft, operational since 1997, and the DSC-OVR satellite, which was launched in 2015. From their vantage point, these instruments measure the solar wind's speed, density, and magnetic field as it flows past them on its journey to Earth. This data provides a crucial, yet brief, window of advanced warning, typically lasting only 30 to 60 minutes before the stream impacts our planet's magnetosphere. It is a narrow time frame that puts our modern world in a constant race against the sun. For satellite operators needing to place their assets in safe mode, for power grid managers reconfiguring transmission networks, or for airlines rerouting flights, a half hour is an incredibly tight margin. Compounding this challenge, our L1 monitors are aging platforms, operating far beyond their intended service lives. Recent observations have even revealed anomalies in their data, suggesting possible instrument degradation. This raises a critical question. When forecasters predict a storm's intensity, they rely on information from spacecraft whose own reliability is becoming uncertain. While newer monitors like NOAA's SWFO L1 mission are planned to replace some of this capability, its launch schedule has faced delays, leaving us dependent on this older generation. For decades, proposals have also existed for monitors at other Lagrange points, especially L5. A mission there would offer a side view of the solar wind, allowing us to see events before they rotate into the Sun-Earth line. Had such missions been flying during recent events, our warning times and understanding of these stream structures would have been vastly improved. But they remain unfunded concepts. Beyond the immediate challenge of real-time monitoring lies a deeper, more fundamental problem: the limitations of our long-term modeling. Our scientific understanding of high-speed streams and their complex interactions with Earth's magnetosphere is built upon models that have been carefully developed and refined over many decades. For typical, well-behaved events, these models perform reasonably well. However, they begin to falter when confronted with the exceptions, the edge cases, and unusual stream structures that defy simple categorization. A significant weakness is their struggle to predict the precise timing of southward BZ intervals. This particular parameter, the orientation of the interplanetary magnetic field, is the primary determinant of whether a solar wind stream will trigger a powerful geomagnetic storm or a minor disturbance. Furthermore, the models have great difficulty forecasting the behavior of recurring streams across multiple solar rotations. This is because the coronal holes themselves evolve, and our models lack the sophisticated ability to anticipate how a specific hole might grow, shrink, or drift across the solar surface over several months. This highlights a frontier where our predictive power is still being forged. The practical consequence of these modeling limitations is that our confidence in any individual storm forecast remains moderate at best. We can predict with reasonable certainty that a high-speed stream is approaching and that a geomagnetic storm of some magnitude will follow. Forecasters can even provide a rough estimate of the KP index range we might expect. What we cannot do, however, is reliably state whether that storm will peak at a KP of 5 or a more severe KP of 7. We cannot confidently say if a critical southward BZ interval will persist for 4 hours or for 14, and looking further ahead, it is impossible to predict with any certainty what the next solar rotation will bring a month from now. This is not a small margin of error. The uncertainty is substantial, and it is not diminishing quickly. The reason for this is that the fundamental physics governing solar wind generation and its interaction with planetary magnetospheres is still an active and evolving field of research. This persistent uncertainty leaves us with profound blind spots in our long-term risk assessment. We are aware that recurring coronal holes are a significant factor, and we understand that they exert a cumulative stress on our technological infrastructure. Yet, we lack the precise quantitative models needed to understand how this accumulating stress unfolds over multi-year timescales. We cannot say with confidence, for example, what percentage of satellite failures in the last decade were caused by repeated exposure to these streams versus other factors. We do not know for certain how much the operational lifespan of power grid transformers has been shortened by the cumulative effects of geomagnetically induced currents. Nor can we confidently calculate the total economic cost of space weather, as so many of its impacts are diffuse, indirect, and difficult to trace. These are not trivial details. They are critical pieces of information we should have to plan effectively for the future, but currently, we do not. What this reveals is a sobering reality about our present situation. The story we are living through this prolonged event of recurring coronal holes and its consequences for the declining phase of the solar cycle is being watched through a monitoring system that is not entirely sufficient for the RECE task. As a global civilization, we are faced with making critical decisions about how much to invest in protecting and hardening our infrastructure against the threats of space weather. Yet, these monumental decisions are being made with fundamentally incomplete information. The choices we make today might prove to be correct, or they could be profoundly misguided. We simply will not know for sure until the consequences manifest over years and decades, in ways that will be incredibly difficult to attribute back to their original cause. It is not a comfortable position to be in, but it is an honest assessment of where we stand. And so we arrive at the central paradox of this entire phenomenon, the story that Calm Space has been tracking throughout this discussion. It is a narrative where predictability and profound mystery coexist in an uneasy balance. We can predict that the coronal hole will return on its next rotation. We can predict that the high-speed stream will arrive at Earth. We can even predict that a geomagnetic storm will occur. The great unknown, however, is how our infrastructure will ultimately respond over time to the cumulative pressure from an environment that we are only just beginning to treat with the seriousness it deserves. This brings us to a crucial, more human element of this story, one that deserves its own focused consideration. There appears to be a significant mismatch between the space weather threats that are of greatest concern to scientists and the ones that tend to capture the public's imagination. Grasping the nature of this disconnect, I believe, is essential to understanding why the phenomenon of recurring coronal hole streams has received so little coverage in the media and in public discourse, especially when measured against its actual, tangible importance. Our fascination with dramatic events is not a modern flaw. It is a deeply ingrained feature of how human cognition evolved. In our ancestral environment, sudden, dramatic occurrences were frequently dangerous ones. A charging lion, a rapidly approaching storm, or a spreading fire were all threats that demanded immediate attention because they necessitated an immediate response. Over countless generations, our brains became exceptionally skilled at recognizing and prioritizing these kinds of dangers. In that world, the potential cost of missing a dramatic threat was death, while the cost of overreacting was merely wasted energy. Evolution, therefore, naturally favored the more alarmed and vigilant mind. This very same cognitive machinery continues to operate today, shaping our perception of modern threats. This is precisely why a coronal mass ejection, or CME, commands public attention in a way that a coronal hole simply does not. A CME is the definition of a dramatic event. Visually, it resembles a colossal explosion erupting from the sun. It generates vivid, spectacular imagery and lends itself perfectly to sensational headlines. The sun explodes, a massive blast heads toward Earth, or experts warn of widespread auroras. The news coverage practically writes itself, ensuring that CMEs remain at the forefront of public awareness, while their quieter, more persistent counterparts go largely unnoticed. When a space weather event occurs, the media coverage that follows heavily shapes our perception of risk. The narrative almost always centers on coronal mass ejections, reinforcing the idea that CMEs are the principal threat, largely because they are explosive and visually compelling. Coronal holes, by comparison, are far less dramatic. They do not erupt. On a solar image, They are merely grey smudges that fail to draw the eye. A headline warning of a recurring coronal hole, potentially stressing satellites over months, gets a tiny fraction of the attention given to a solar flare. This results in minimal coverage, which in turn keeps public awareness low. When the public is unconcerned, political attention remains elsewhere, and the funding needed to improve our resilience is never prioritized. This feedback loop is the signature of what can be called a slow disaster. This pattern of overlooking gradual danger is not unique to space weather. It appears to be a fundamental blind spot in our collective awareness. We see the same dynamic with climate change, where the slow accumulation of risk is systematically underreported compared to specific acute weather events. It is the same with infrastructure decay, where the gradual deterioration of bridges, water systems, and power grids receives far less attention than their sudden failures. We also see it in the rise of antibiotic resistance, a threat that develops over years while media cycles focus on immediate outbreaks. All these phenomena cause immense cumulative harm over long timescales, yet their mechanisms do not create compelling, immediate stories. As a result, our collective response to them is chronically insufficient. The recurring high-speed streams from coronal holes fit this pattern perfectly. The threat they pose is methodical and regular, its effects are cumulative, and its appearance is anything but dramatic. This makes the story difficult to tell without sounding needlessly alarmist. And yet, the risk profile, as we have been exploring, is substantial. A new cycle of stress is placed upon our orbital infrastructure every 27 days. With each rotation of the Sun, satellites absorb another cumulative dose of radiation, testing the very limits of their design. With every recurrence, the probability of a critical failure somewhere in the system quietly increases. The greatest obstacle to addressing this may be the psychological mismatch between the scale of the risk and the minimal attention it receives. It is worth imagining how different our situation would be if we viewed these coronal hole streams the way we view hurricanes, as a recurring, seasonal threat, demanding careful planning and preparation. If that were our mindset, we would be in a profoundly different position. We would likely have superior monitoring systems and hardened infrastructure. Our emergency response procedures would specifically account for multi-event scenarios. We would see insurance products priced with an understanding of space weather cycles, and regulatory frameworks would require satellite operators to prove resilience against cumulative exposure, not just isolated peak events. In short, we would be treating this threat with the seriousness it deserves. But we do not take these steps, because to most of us, the threat simply does not look like one. It appears as a faint grey smudge on a solar image, accompanied by a technical advisory that most people will never even see, let alone read. What will it take to change this perception? Perhaps it will require a more compelling narrative, a more visible and disruptive failure, or a more concerted effort from scientists and communicators to connect the dots between that smudge and its real-world consequences. Until that shift occurs, we will likely continue to live in a world where the loud, explosive threats command our attention, while the quiet ones are overlooked, even when they are the ones causing more of the damage over time. Part 18. The Real Shift in Space Weather Risk. If you have journeyed with us this far, you now possess a picture of the situation that is significantly more nuanced than what a typical news article about the current G2 storm watch could provide. You can now see that the event unfolding is not an isolated incident, but a predictable event in a recurring cycle. You understand that the mechanism of damage is not just the intensity of a peak storm, but the cumulative exposure of our satellites and grids to months of repeated stress. You know that the forecasters issuing these advisories are working with incomplete data, aging monitors, and models with very real limitations. you grasp that the declining phase of the solar cycle is poised to amplify all of this, and that the infrastructure we rely on, which was not designed for this environment, is beginning to show the strain. With this foundation, we can now synthesize what this all means in plain terms, a fundamental shift in how we must think about space weather risk. The traditional model has always been episodic. In this view, events happen and then events end. In the quiet periods between them, the system has time to recover. Risk, therefore, is determined by the frequency and intensity of these discrete events. This model is not incorrect for coronal mass ejections, which are by their nature episodic. They erupt, travel, impact, and then dissipate, with each one representing a self-contained event. But a new model is emerging, one that the relentless nature of recurring coronal hole streams points toward. This model is not episodic, it is continuous. The events are frequent enough, and the intervals between them so short that the system never fully returns to its baseline state. This has profound implications. The radiation belts never completely drain, satellite dielectrics never fully discharge their built-up charge. Transformers on the ground never have a chance to fully cool. The ionosphere never truly stabilizes. The environment becomes one of continuous, low to moderate disturbance, punctuated only occasionally by the acute spikes of CME-driven storms. In this perpetually stressed environment, the very nature of the damage mechanism changes. It shifts from a focus on peak loads to one of cumulative stress. As we have discussed, this presents a fundamentally different engineering problem. Under the old episodic model, the philosophy was to design systems to withstand peak events and then simply ride out the quiet intervals. Under the new continuous model, however, one must design for chronic stress, while assuming that occasional peak events will push that chronic load over an acute failure threshold. These represent two entirely different design philosophies, leading to different kinds of infrastructure, different operational procedures, and different investment priorities. The critical issue we face is that our current infrastructure, for the most part, was built under the assumptions of the episodic model. It is now set to face its greatest tests under the demanding reality of the continuous model. This mismatch between design and reality lies at the heart of our modern vulnerability. There is, however, a version of the future where we adapt to this shift with foresight and grace. It is a future where we upgrade our monitoring capabilities, harden our satellites against long-term exposure, build more redundancy into our critical systems, and develop more sophisticated predictive models. This path requires acknowledging the new reality we face and acting decisively to prepare for it. The expense is significant, yet it remains manageable, spread out over many years and amortized by a growing space economy, the very economy that generates the value to justify such an investment. In one version of the future, these recurring coronal hole streams become a known variable, a factor that is planned for, allowing their impact to be minimized. But there is another version, one where we fail to adapt in time. In this scenario, the recurring stress accumulates faster than our ability to reinforce our systems. Satellites begin to fail at rates higher than anticipated, and entire constellations degrade. The services they provide grow less reliable until critical failures cascade through our deeply interconnected infrastructure. While the economy absorbs these losses, they are far greater than they needed to be. It is only then, in the aftermath of a preventable crisis, that we finally make the investments that, in hindsight, should have been made a decade earlier. Which of these futures we inhabit will be determined by choices being made right now by satellite and grid operators, by regulators and governments, by researchers and communicators. The storm arriving in the coming days, this specific coronal hole event, is but a single data point in that much larger decision. It is, however, a data point that fits a pattern one that has been visible for some time and is only growing clearer as the solar cycle evolves. This pattern is quietly, yet insistently, asking us to take recurring space weather seriously. This brings us back one last time to the contradiction that began this story. A storm warning without a storm, a coronal hole without a visible hole, and a dangerous event without a single flash of light. The absence of spectacle, upon closer inspection, turned out to be the drama itself. The true danger was never in what we could see. Instead, the hazard lies in what is continuously, predictably, and invisibly flowing from the Sunday. This stream rotates into view every 27 days, adding its contribution to a cumulative burden that our technological infrastructure was never truly designed to bear. This is the shape of the threat we have been circling. It does not announce itself with a brilliant flare or a loud noise. It does not light up our cameras or trigger our sirens. It simply arrives, does its work, and rotates away, leaving behind a system that is a fraction of a percent more stressed than before. Then, a month later, it returns to do it all again. The coronal hole, currently directed at Earth, will rotate out of our line of sight over the next few days. As it does, the solar wind stream will taper off, the geomagnetic storm will subside, and the KP index will fall back towards zero. In the radiation belts, the flux of energetic electrons will modulate, likely dropping from its currently elevated levels as the stream passes, only to rebuild in the days that follow. By the end of April, the immediate event will seem to be over. The auroras will fade from the sky, and the headlines will move on, as headlines always do. Media coverage will shift to the next sensational story, a political drama, or a new coronal mass ejection, should one happen to erupt. And so, the quiet, persistent, recurring threat we have spent all this time examining will slip back into the background. It will return to the place where it has always lived, unreported, unacknowledged, and unchanged. Somewhere in the sun's corona. That very same coronal hole, if it persists through its 1-3 and a half-day journey across the far side, will rotate back into view on the eastern limb in early May. At that moment, the cycle will begin once more. This is the inevitability of the situation. The event is going to repeat. It has repeated countless times before, and it will repeat again. It is a process entirely indifferent to our news cycles and our fleeting attention spans. It does not care whether we have built the monitoring infrastructure to track it or the engineering resilience to withstand it. The cycle will continue regardless. The only real questions are how long this particular structure will persist, how many rotations it will endure, how the geometry of Earth's magnetosphere will respond over that time, and how the cumulative damage will ultimately play out across the systems we all depend on. These are not questions we can answer with certainty right now. They are questions that will be answered only by what happens, month after month, storm after storm, cycle after cycle. We are living in the middle of the answer, and we do not yet know how it ends. It is a strange position to be in, if you allow yourself to feel it fully. We are not watching a documentary about something that has already concluded. We are living inside the experiment as it runs. What we do know is that a fundamental shift is happening. The solar cycle is transitioning into a new phase where coronal holes are becoming more active and better aligned with Earth. These recurring streams are starting to dominate the space weather landscape. Consequently, the infrastructure we rely on is being stressed in ways that our design philosophies are only now beginning to address. And the very monitoring systems we need to understand all of this are themselves aging and imperfect. The ACE and Discover spacecraft are old, and their replacements are behind schedule. The models that translate raw solar wind data into useful forecasts are working with assumptions that were established during a different era of solar behavior. We are navigating a significant change in our space environment with tools built for a different time, and we are doing so in real time. This is not a comfortable position, nor is it one that offers easy answers, but it is the honest position, and it is better to face an honest uncertainty than to embrace a neat conclusion that cannot withstand scrutiny. So, the question I want to leave you with is not the one the headlines usually ask. The headlines pose questions like, will it hit Earth? How bad will the storm be? Or, will we see auroras at lower latitudes? These are interesting questions, to be sure. They are the questions that generate clicks, produce compelling graphics, and fuel news segments. And if you are hoping to photograph the northern lights from an unusual location, you certainly want to know the answers. But they are small questions when compared to the one that truly matters. They treat each solar event as if it exists in isolation, as if the only thing of consequence is whether tonight's sky will light up. This perspective misses the larger, more profound truth. We are not just witnessing an event, but a continuous, unfolding process that demands a deeper understanding. The prevailing question is not what occurs when the sky ignites for the 30th time in a year, following the 29th, the 28th, and a decade of cumulative damage that went uncounted. Instead, the question that truly matters is one of resilience. It is a question of repetition, of whether the intricate systems we have built, the very systems that underpin modern life, can absorb the grinding, recurring pressure of an environment that is slowly but persistently stressing them beyond their design limits. After all, a single storm, even a powerful one, is seldom enough to break a well-designed system, but 10 storms in a year, each arriving before the effects of the last have faded, could be a different story. 100 storms over a decade, each one bombarding a satellite fleet with more cumulative radiation than its engineers ever planned for, almost certainly will be. Somewhere within that sequence, during one specific solar rotation, a threshold is crossed. It might be a transformer on the power grid, slowly degrading over time, that finally gives way during a storm it would have otherwise survived. It could be a satellite that has been accumulating electrical charge in its dielectrics, cycle after cycle, until it suffers the one discharge that takes it offline forever. Or perhaps it is a GPS constellation which has been losing its redundancy one node at a time, that finally drops below the minimum coverage required to deliver the precision we have built our lives around. The essential question is how many events it takes to reach that point. It raises a more immediate concern. How close to the edge might we already be, and will we even see the failure coming? The answer to that last question, perhaps, leans in a direction we would rather not contemplate. The nature of cumulative threats is that they do not announce their arrival. They send no warning. They simply reach their breaking point quietly, on an otherwise ordinary day, and the thing that was supposed to keep working suddenly stops. In the aftermath, everyone looks around, asking what just happened, as if the failure materialized from nowhere. But it did not come from nowhere. It came from the sun's 2 7-day cycle. It came from the rotation before that, and the one before that, each adding its small contribution to a load that nobody was adding up. We seem to be conditioned to search for a single, dramatic cause, when the reality is often a slow, invisible erosion. This brings us to a fundamental reframing of the issue. The real question is not whether the sun will hit Earth. That was always the wrong question. The sun has been striking our planet continuously for 4.5 billion years, and it will continue to do so long after we are gone. The only thing that has changed in all that time is us. In the last 50 years or so, we have built a civilization whose entire nervous system exists in orbit. We have placed our eyes, our ears, our timekeeping, our navigation, and our communications into a fragile layer of machinery drifting through a hostile environment. It appears we did this without fully accounting for what that environment truly does. Now, we are learning in real time what it costs. The real question is, how many times can it hit before something breaks?